Hello, in this video we're going to talk about the Global Positioning System, also known as GPS. So by this point of the class, you really have focused on a lot of different methods, and I have of taking points and their relevant information, be that their distance between each other, their elevation, the angles within a closed traverse or an open one. We've done it with a number of different ways. We've talked about mistakes versus errors. We've talked about precision. We've talked about accuracy. And it's all come to this. So GPS is every surveyor's dream. They've been basically working towards that for ages. And I think from the beginning of humankind, humans have looked for an accurate way to find information about the spaces they live in. And with GPS, we have an extremely accurate system. So in many ways, everything that we've covered so far is semi-obsolete. Now, don't be angry at me. Thanks to all of those steps, the different methods that we use, whether it was a total station or a theodolite, an automatic level, or a plain old pulling chain using steel tapes, GPS is only, you will only be able to understand GPS clearly and its implications in field work if you've gone through that whole process. So it is really, and really GPS has multiple purposes, but in a way it may turn out to be the greatest surveying tool ever developed because you can quickly and accurately find points located on Earth by measuring distances to artificial satellites. So satellites have been a major game changer in this field. Okay, so where did this all come from and why? So it seems like putting a ton of satellites in the atmosphere for surveying purposes seems a little bit of overkill. Well, that's because it really started with something involving, of course, war. In 1978, the Department of Defense, so the DoD, began to launch satellites into space with the goal of being able to quickly and accurately locate positions on the Earth. So this system was secret for a long time, and then of course Soviet military aircraft figured it out, and blah blah blah, sad story, President Reagan. It's actually a really interesting story, just not exactly the point of what we're trying to talk about today. However, soon after this happened in the 80s, President Reagan did announce that GPS would be made available for civilian uses. So 85, I mean, so that sounds to you guys, some of you guys that were born in the 90s, like long time ago, but in reality, we're talking about 30 years ago. I mean, this technology has changed surveying and has changed it forever. And it's very recent. So by 1985, there were 10 initial Block 1 experimental satellites, and in 1994, there were 24 Block 1, and then there were more modern Block 2, etc., etc. So nowadays, we have a really reliable system. Each satellite tries to fly by the Earth in a straight line at about 8,650 miles per hour, but the gravitational force of the Earth pulls it down. So as a result, the satellite falls vertically in a path that it is parallel to the Earth's curved surface. And if the satellite's velocity were decreased, it would fall into the Earth. And if it were increased, it would leave the Earth and move further out into space. So, yeah, anyway, I was getting ahead of myself. So, all in all, GPS satellites are in a medium Earth orbit, approximately 12,600 miles above the Earth's surface, and where their orbits are completely free of the Earth's atmosphere. They are located in orbital planes that are inclined 55 degrees to the equator. Okay. The initial satellite constellation was manufactured by Rockwell International, which is now part of Boeing, and they weighed about 1,900 pounds each. So anyway, each satellite broadcasts its orbital position as a modulated signal. Then how does this work? Well, then we have a receiver that determines the difference between the time signal from the satellite and its own internal clock. So this is really interesting because these clocks are extremely precise, and the way that this was figured out is actually really interesting outside of the scope of this class, but let's just say that this was quite the marvel of engineering. Okay. So all in all, the way that this works is that the distance from the satellite can be calculated using the speed of light. And of course, you need several of these satellites in order to triangulate your coordinates. You can't just go by one, you need at least 3 or 4. Now the system that we're talking about, and there are several, but one of them is the NavStar system, which stands for Navigation, Satellite Timing and Ranging Global Positioning System, excuse me. But we use GPS, it's shorter. So now the American NavStar GPS system is now part of a network of satellite-based positioning systems that currently exists. And this network is known as the Global Navigation Satellite System, or GNSS. So, let me see. So the Global Positioning System is composed of 24 satellites plus a few spares and 5 control stations, which are found, actually here there are, no, there's 5. Sometimes some of these places have a couple of extra that are kind of supporting some of these. So there's a Hawaii one, there's one in Colorado Springs, which is the Master Control Monitor Station, one in Ascension Island, one in Diego Garcia Monitor Station right here, and one, I actually know how to pronounce that because I've had friends that have lived in that island, Kwajalein. Kwajalein is where SpaceX started first testing rockets, in case you've ever wondered that. You can look it up. But anyway, these are strategically placed, and you can sort of see it here. Actually feels like the one that's kind of out of this beautiful circle here is this one. But of course, the master station needed to be in the United States because we came up with this stuff. Okay, now let's talk about GPS uses. So the first use is military. It was originally designed for military positioning situations in times of war and peace. So it's a strategy thing. And then once it became available for everyone, it became a surveying tool. So GPS really has become a common tool for any surveyor today. And you can get really good quality GPS receivers. Now they're very, very, very expensive, which is why MCC will probably never have one. And that's okay. We can, thankfully, City of Waco lets us, gives us a demo every year. Or someone else. We find someone to give us a demo, actually. One year was SpaceX. Anyway, so GPS can be used in all types of survey, including land, construction, topographic, route surveys, etc. And now, remember how it used to take a team of 4 with steel tapes and plumb bobs and hand levels to survey a property, and it would probably take the better part of a whole day just to do the basics. That's only doing distances, not even doing angles or anything like that. Yeah. So nowadays, a single surveyor can accomplish all of that in a day, what used to take maybe weeks. And there are a number of reasons why many surveying operations can be done more efficiently with GPS. So one of the reasons is that it is not constrained by line of sight visibility issues. So this is an issue we encounter on and on in lab. Is if you can't see the point, you have to create this extra point, and it's more work if there's a tree in the way or if there's some sort of structure. So with GPS, this is not an issue, except there is an issue with being inside places. So we'll talk more about that in a minute. Also, so now the spacing between stations can be increased, and internal calculations can take the curvature of the Earth into account. So this class is called plane surveying, and we did say that we would not be surveying anything longer than, say, a mile, because once you start getting to a certain distance, you will start having the curvature of the Earth be an issue. But with GPS, that's already taken into account. And weather is also not a big issue. You also know that if it's horribly raining or thundering or anything like that, you can't take survey points. GPS doesn't care. Okay, so now the general public can use it for a number of things, and it's not just surveyors. As public, we ourselves use it every day for navigation purposes. We use it for GPS, although when you think about surveying GPS units and like car GPS units, they're completely different, even though they're based on the same satellite system, because their precision is completely different. So in a car, I think the precision is like I think you're good in like a 10 feet radius or something, which is pretty good considering. But in surveying, clearly being here or 10 feet away from here, it can be an issue. So it's used, I mean, by hikers and hunters and bikers. There's all these apps locating places and things, and of course geocaching. If you've never gone geocaching, I recommend it. Just feed your inner nerd and go look for treasure using GPS coordinates, and there's all these fun apps. And by treasure, I mean stuff that you can buy at the dollar store or one of those 25-cent machines outside of Toys R Us. But you know, it's actually really fun. You get to collect stuff. You think I'm joking, but I'm really not. I've gone geocaching. It's actually quite fun. Okay, let's continue. GPS basic theory. So there's this definition of satellite ranging that you need to know. Satellite ranging is the measurement of distances from a position on Earth to satellites. And look at this pretty picture right here. We have Earth, and we have this set of 24 satellites going around in specific orbits in a way so that any point in Earth, for the most part, is covered by quite a few, can be seen from quite a few satellites. So the idea is the following. We have a point in Earth. So the satellites are at known points orbiting the Earth. Their range is defined by the difference in time between sending and receiving a signal. So using resection trigonometry, the location of the receiver clock can be calculated. And most errors in the range of intersection are due to error in the receiver clock, not the sending clock. But anyway, even this, I guess there can be major malfunctions, but on the most part, these things are like extremely precise. So now look at this. So we had 3 over here. Well, what about a 4th one? So one of these actually measures, locates me at any point along the circle. So it basically, if let's say this was the first circle right here, well, you could be anywhere around here. Next, once you do 2, let's say this one and this one, those 2, or no, actually this one and that one. Those 2 narrow the position to only 2 points. So if it's this one and that one, you could be somewhere over here or somewhere over here. Once you get the 3rd one, a 3rd radius will narrow it to clearly it's this point. And the 4th one, if the timing offset is consistent, the 4th radius measurement will compensate for the errors. Okay, so it's kind of to check. So clearly you're here. All right. Let's talk about limitations and sources of error. So clearly this is not perfect. It's very accurate, but there's no such thing as a perfect measurement. GPS without correction can only provide an accuracy of about 20 meters. However, satellite signal and also satellite signals cannot penetrate water, soil, or walls. So this is the one. It's like line of sight is not an issue, but you also can't like measure a point on the other side of the Earth that the satellite's not directly kind of looking at. So line of sight is an issue for the satellite itself, but when I was saying line of sight, I mean between the points themselves. And it is difficult to make GPS observations in heavily forested areas, actually, just because, again, penetrating like really deep forest. But there's antennas, so you can make an antenna stick out, and that will make it work. So potential sources of error. Atmospheric error, so that's atmospheric corrections are incorporated, but the atmosphere is not homogeneous and changes constantly. Multipath error is when signals reflected for other objects can cause time to increase slightly and decreasing accuracy. And I have a picture of that, I think, or there's one in your textbook. Satellite error, although satellites do have very accurate atomic clocks, slight errors in their measurements can cause large errors in distance calculations. And other sources, you can have a receiver quality or setup, microwave or other radio interference, blunders, oh, I already had said that, wrong set of parameters, or power source issues. Now, here's where I tie all of this in. You need to understand measurements in order to understand what the GPS is spewing out, because if you don't understand measurements and what they mean and errors and all of that stuff, whatever the GPS tells you, you're just going to trust and write down. Instead, now as experienced well, I wouldn't call you experienced surveyors quite yet, but with people with experience with measurements, you could see a measurement and be like, wait a minute, that doesn't seem right. That doesn't make absolutely any sense. Clearly, this is not 200 feet. And you can look for errors and maybe fix a bunch of data before you do all that work, only to realize that at the very beginning you made a boo-boo. Oh yeah, so here, so let's say that you're trying to measure, this is a multi-path error. So let's say that the receiver is here and this is your satellite, and sometimes as it's looking for this, it bounces off of a building or something, so it causes an issue, and it becomes, however, what happens is if something is blocked, it has to connect with another satellite and then bounce it off so they can see it, or use another, like this one would have to do the multipath signal, or then this one can see it directly. So these GPSs are designed and programmed to be very smart about things like that. Okay, we're gonna stop this right here and we're gonna continue over in a different video, just so that this video doesn't get too terribly long.